Okay, hello everybody. Hope everybody is doing okay. So today we're going to be talking about the group work in Unit 8. So first of all, any questions, comments, anything that you'd like to be clarified?
I do have a quick question.
Yeah.
So this is kind of related to the homework, but I believe it's also related to the group work too.
Yeah.
If we define like a set to have 1, 2, 3, 4, 5, and we say that, like m is equivalent to n or is similar to n if m minus n is equal to 2.
Uh-huh.
Right? So if 5 minus 3 is 2 and 3 minus 1 is 2, can 3 appear in two different subsets?
So that's a great question. Let me share the screen and write as a answer but I'm going to ask you right away. Is what you just described for me an equivalence relation? Okay, think about it while I set up this thing.
Okay.
Share, go. Okay, so let me go down here. It's going to be saved for later. And so the question, let me write it for everybody, is suppose that x is equal to 1, 2, 3, 4, and 5. And in the equivalence relation, you said m is equivalent to n if and only if, or the rule that you claim you would like to be an equivalence relation, if and only if m minus n is equal to 2. So my counter question, so Tyler's question is, by this rule, 1 is equivalent to 3. 3, or sorry, that's wrong. By this rule, I have to be very careful. Three is equivalent to 1, and 5 is equivalent to 3, right? But 5 is not equivalent to 1, right?
Yep.
So then my counter question is, well, then is this an equivalence relation?
I don't think so. And because it doesn't, I forget, it's T. I forget what the name is. But
yeah.
It doesn't fill that requirement.
Yeah. So tilde is not an equivalence relation because what we just talked about is a counterexample to the holding of the transitive axiom. Okay, so other question is what other axiom, well, does any of the axioms of equivalence relations hold? So T does not hold. But does R hold?
No.
Right? R does not hold, right? Because 3 is not equivalent to 3 because 3 minus 3 is not equal to 2.
Right. So every equivalent relation has to fulfill the R, S, and T rules always, and then like m equivalent to n is equal to, or if m minus n equals 2, it's just like a fourth rule.
So this one is some rule, right? Some rule of squiggling, if you want, right? Which does not fulfill the requirements to be called an equivalence relation.
Okay.
This is some rule, but is not, does not deserve to be called an equivalence relation.
Okay.
The same way that if you, if you say, okay, I'm giving you something that I want, I would like to call function, but f of, the number 1 is going to be 5 or 7 sometimes, right? Then I would tell you like, well, then that rule that assigns to the input 1 the output 5 sometimes and 7 other times, it's a rule of assigning outputs to inputs, but it's not a function because the same input can have multiple choices for output.
Okay. Okay.
Okay. Cool.
Yeah, thank you. That helped a lot.
You bet. Thank you. That was a really good question. All right. Any other questions, comments? I should try to pull out the chat so that if you're writing, I can see it. Yep, nothing there yet. Okay, well, if there's no questions, then I'm going to be the one asking some questions. So let's go over the group work together.
Like...
Let's maybe start. Oh, 8.5. We will definitely get there, but I want to start at the beginning. So let's start talking a little bit about 8.1. Right. So one thing is, how do you, there's 2 steps to a question like 8.1. One is to understand what the question is asking, and the one is how to write a formal proof, right? So for example, if we look at right here, 8.1, and let's say if we have a rule of squiggling that says that m wants to be equivalent to n if and only if m minus n is even. Okay. And the question is, does T hold? Right? Does the transitive axiom hold? So that is this, right? So to understand what's going on, my recommendation is to do some example, right? So for example, let's see if I can get this to scroll. Nope. Oh, I love technology. Microsoft. So, for example, right, say, okay, well, I know that 2 is equivalent to 6 because 2 minus 6 is minus 4 is even, okay? And I know that 6 is equivalent to 18. So does that imply that 2 is equivalent to 18? And the answer is yes. And why is this? Because, well, if the difference between 2 and 6 is even and the difference between 6 and 18 is even, then the difference between 2 and 18 is the sum of the 2 differences, which is the sum of 2 even numbers, which is also even. Okay? So the example has helped me to understand what's going on, but that's not what goes in the proof, right? So what goes in the proof is the understanding that the difference between 2 and 18 is the sum of the difference between 2 and 6 and 6 and 18. Okay, so let me see if I can reset this thing so it doesn't slide. Okay, it erased everything. Great. So let me rewrite this. M is equivalent to n if and only if m minus n is even. And the question is, prove that T holds. Okay, how do you prove it? So the proof So T is an axiom that has a for every statement, right? So you have to assume that you have three numbers. M, N, and maybe P, right? Such that okay, there we go. Such that M is equivalent to N and N is equivalent to P. Okay, so first thing is write down what it means for M to be equivalent to N. M equivalent to N means that M minus N is an even number, so it's 2k for some k, an integer. N equivalent to P means that N minus P is equal to 2, again, j for some integer. And now what we want to show that M is equivalent to P, i.e., we want to show that N minus P is even. Okay. So now how do we use the hypothesis to show that M minus P is even? Well, we say, well, M minus P is equal to M minus N plus N minus P, right? Because the N in the middle cancels, which therefore is 2k plus 2j, which is equal to 2 times k plus j. And because k and j are both integers, then k plus j is an integer, so this is even. And so this proves the fact. Okay, so this is, and it's going to be on the notebook, so then I'll share it so you can look at it. But this is how you formally prove it. I saw many groups just wrote about, a few examples. That's not a proof, right? The proof has to be done symbolically because it has to hold for every three numbers, M, N, and P. You don't get to choose your three favorite ones. Okay, so if that's okay, give me a quick yes or no on the chat. Be good to move on. Okay, great. Thank you, everyone, the people that say yes. So I wanted to talk a little bit about problem 8.3. So let me pull out a little drawing device. So problem 8.3 said, okay, if I give you a function f from x to y, there's a natural equivalence relation that you can put on x by saying that x1 is equivalent to x2 if and only if f of x1 is equal to f of x2. Okay. So question for everybody that you can unmute yourself or answer in the chat. is what are the equivalence classes, what are the subsets in X that are equivalence classes for this equivalence relation? So I can, it's easy to draw them, right? It's 1, 2.
Yeah, 8, 5. Oh.
Oops, 4 was not there. Sorry. 1, 2, 8, 5. There's 1. There's 4 and 6. And 3 and 7. But what I'm asking is not what they are in this example, but what other name can we give to these 3 subsets?
Is it the inverse image or?
Yeah, right? So 1, 2, 5, 8 is the inverse image of the singleton A. And 4 and 6 is the inverse image of the singleton B. And 3 and 7 is the inverse image of the singleton C. Okay? And so if you remember last week, we proved that like the union of the inverse images of the elements of the output set always gives all of X, and no 2 inverse images that are distinct intersect. Well, that is exactly saying that the inverse images of the singletons consisting of the elements of Y form a partition of the set X. And now we know that a partition is the same as an equivalence relation. So hopefully this is good. So how many equivalence classes do we have now for this equivalence relation? So the quotient set has 3 elements. Right? These 3 elements have many different names. For example, this dot here, I can call it the equivalence class of 2 or the equivalence class of 1. I can also call it the equivalence class of 5 or 8, but these are all different names for the same element of the quotient set. This dot here, I can call it the equivalence class of 4, but same name for this element is the equivalence class of 6, and this is 3 or 7.
Is there a name for the elements within that set?
Within what set? Sorry.
With the equivalence set. So the one we're labeling right now. Is there like a specific name?
The name for the elements in this set are just equivalence classes of in X.
Okay.
Right. And so the problem is not that having a name, is that you have too many names for the same element.
Yeah.
Right. So you have an element here with 4 names.
Okay.
But it's this is it gets a little bit better if you really think of the square brackets as meaning the way you read equivalence class, sorry, the way that you read square brackets is the equivalence class of. Because now it doesn't shock you that it's possible that square bracket 1 is equal to square bracket 2, because that's saying that the equivalence class of 1 is equal to the equivalence class of 2, but that's this, is exactly the same statement as saying that 1 is equivalent to 2. Okay. Hopefully that helped. Right?
Yeah, that makes sense.
Okay, great. And now the question was, okay, we can create a new function. Right, let's call it square bracket f from x mod tilde to y by the prescription that square bracket f of square bracket x is equal to, just ignore all the square brackets, f of x.
Hey,
Okay.
Renzo, can you scroll down a little bit?
Can I scroll down? I'm afraid I can't with this screen, but maybe I can write things up here. So square bracket f of square bracket x is equal to f of x. Is okay?
Yep.
Okay, so let's parse this thing a little bit, right? So square bracket f is a function whose input set is x mod tilde, and its output set is y. Right? So it takes as inputs elements down here. So for example, let's see what the input for this dot is. And the way that assign, no, the output should be in y. And the way that it assigns an output to this dot down here is, it tells you like, well, look at any one dot in x whose equivalence class is this dot in here, and then follow f from there, right? So in particular, this dot right here is the equivalent class that 1 belongs to. 1 is mapped to A, so this dot should go to A. Okay. Now, of course, we need to worry, right? We need to worry because, you know, we used 1 to see where to send this dot, but we could have used 2, we could have used 8, and we could have used 5, right? Because these are 4 different names for this dot. But luckily, by construction, 1, 2, 8, and 5 are precisely all the elements that go to 8. Okay? So regardless of what x you use to decide where this dot down here should go, you're always going to end up at 8, at A, at the letter A. Okay.
Can I ask a quick question once you're kind of done here in reference to, because I feel like this relates to 8.7 with,
Yes.
is the, okay.
Yes.
So once you're done, I'll have a question.
Okay. So let's finish real quick, right? So 4 and 6, well, the equivalence class of 4, which is equal to the equivalence class of 6, will go to the image of 4 or the image of 6, but both are B. And similarly, this dot is going to go here. Okay. And now it's immediate to see that this function is a bijection between the quotient set x mod tilde and the set y, because x mod tilde has 3 elements, y has 3 elements, and each dot of x mod tilde goes to a dot of y, but vice versa, you can reverse the direction of these arrows. You can send A to the equivalence class of 1, B to the equivalence class of 4, and C to the equivalent class of 3. And this is also a function, so the function is invertible, so it's a bijection. Okay, so hopefully, save this. Hopefully this is good. Any questions? Okay, so was it?
It was me.
Was it
Tyler? Yeah.
Tyler? Okay.
Go
ahead.
So from that image, or I guess let me read 8.7 real quick. But 8.7 just says, when is a function from x to y equivalent to f brackets times or dot the partition function, or bracket f from x mod tilde to y. And that's only true if there's a bijection between the two, the x mod tilde and y, correct?
Sorry, can you repeat for a second? Are you wanting me to look at 8.6?
Oh, sorry, 8.6. Yes, I said 8.7. I meant 8.6.
Okay.
Yes.
8.6. Okay, so that's a little bit different, right? So let me.
Okay.
I've actually prepared a picture for this. So let's jump there. That was sort of the beginning of my notebook. This is actually the function, the example in problem 8.5.
Yep.
Okay. And we can still try to have a prescription like this that says, how about we define a function from the quotient set of x mod this equivalence relation to y by just removing the square brackets, right? And so the question is, in this case, does this prescription that I highlighted in yellow define a function from x mod tilde to y?
I don't believe so.
It doesn't, right? Why not?
Because you have equivalent elements mapping to different things.
Exactly, right? So the answer is no. And the reason, let me write it here. The reason is that 1, the equivalence class of 1, is equal to the equivalence class of 2, right? So 1 is equivalent to 2, which implies that the equivalent class of 1 is equal to the equivalent class of 2, but square bracket f of square bracket 1 by this prescription, right, is b, and square bracket f of square bracket 2 by this prescription is a. So this rule assigns two different outputs to the same input. Okay, so the problem is not so much that the function is or is not surjective, because you see here now the function f is surjective, but the square bracket f is not a function. And also, I mean, I could add elements here. Now my f is not surjective anymore, but square bracket f is still not a function, right? So it's not an issue, with f being surjective, right? The issue is, like you said, is that you have two elements that are equivalent that are mapped to elements of y that are different, right? So the condition that we're looking for talk about 8.6.
Can I interrupt real quick?
Yeah.
So can you scroll back up to that picture real fast?
Yeah.
So let's say that we changed the red dotted line to not include 1, so just 5, 3, and 7 were in the top part. Because we have them circled in different green circles, but because all of that would map to B, could we say that they're equivalent? like 3 would be equivalent to 5 because it maps to the same y?
No. Sorry, be careful. So
Okay.
the different situation between what we did before, what we did here, right, and what we're doing here.
Okay.
So in this example, we created an equivalence relation from the function f.
Yes.
Right? I did not give you an equivalence relation a priori. I said, here's a function f. Now use f to create an equivalence relation of x by taking the equivalence classes to be the inverse images of the singletons of y.
Okay.
In this example here, the green sets are an equivalence relation on x that is born before the function f. So I've given you now x with the green bubbles, right? And this equivalence relation has nothing to do with f, right?
Okay.
And then I gave you an f that says send the even numbers to a and the odd numbers to b, right?
Mm-hmm.
And then what happened is, well, maybe to be expected, that because this equivalence relation is born without having any relationship with f, right, that f does not induce a function from the quotient set of x with respect to this equivalent relation.
Okay. Yep. That clears up a lot for me. Thank you.
Yeah. So if, now you can do a couple things. You can change the f, or you can change the equivalence relation so that things work, right? But the key point is that there must be some condition, some relationship between f and the equivalence relation for this square bracket f written here, highlighted here in yellow, to actually define a function.
Okay. Thank you.
And this condition is, let's write it. So that f from x to y be a function and let tilde be an equivalence relation on x. And at this point, f and tilde, are not related in any way, right? Then square bracket f of square bracket x being equal to f of x defines a function square bracket f from the quotient set x mod tilde to y if and only if, so the following relationship, okay, today I'm hating Microsoft, does random things like changing colors of pieces. If and only if, for every, actually let me say it another way, x1 equivalent to x2 implies f of x1 is equal to f of x2. Right? Because x1, why is this the case? Well, because x1 equivalent to x2 means that they belong to the same equivalence class. So x1 and x2 correspond to one element only in the quotient set. And so functions, if you have only one element, you have to have only one output. Okay. one input. So it must have only one output. Okay, does this make sense? This is pretty important and can be pretty confusing. So again, if it makes sense, give me a yes on the chat, and if it doesn't, give me a no or a maybe. Got a couple yeses. Okay. Great. Cool. All right, so I want to talk a little bit about what we learned from problem 8.3 and that we're applying to problem 8.5 and 8.6, right? So in problem 8.3, let me go back to this picture. We started with a function. We created an equivalence relation on X, and we obtained a bijection between the quotient set and Y. Okay, so if you remember last week, we said injective functions are essentially the same concept as subsets, right? In the sense that every time you have an injective function, you get a subset, which is the image of the input set inside the output set. Vice versa, every time you have a subset, you can just think of a subset as the input set itself and the inclusion function that just sends every element to itself, and that's an injective function, right? And then we said, okay, we want to find a similar statement for surjective function. And now we can really fill this in more appropriately. The object that is associated to a surjective function is an equivalence relation. And this is, again, in the sense that given a surjective function, you can produce an equivalence relation. So let me say surjective function f from x to y. You can induce an equivalence relation on x. How do we do it? You just define x1 equivalent to x2 if and only if f of x1 is equal to f of x2. And further, this equivalence relation produces, naturally gives, a bijection between x mod tilde and y, right? So y is in a sense identified with the quotient set, and this bijection is given by the rule that we just talked about, f of the equivalence class of x is just equal to f of x. Okay, so let's spend a few minutes. So I hope the statement is making sense. If not, please, scream or type something. I want to spend the next few minutes formally proving this statement, showing that it's true, right? But what we're going to be doing, we're just going to formalize what we've done here in this example, right? Constructing these 3 vertical lines or diagonal lines between the equivalence class of 1 and A, the equivalence class of 6 and B, the equivalence class of 3 and C, right? We're going to write what we did here in general, right? And we're going to prove why it works in general. Okay. I don't see anything in the chat telling me to stop yet. So hopefully this means that. So the first thing to check is that f is a function. Okay. But what does it mean to check that f is a function? Well, if you have one input, you have to have exactly one output. And we said right here that the condition for f to be, for square bracket f to be a function is this one right here. Let's call it star. That every time x1 is equivalent to x2, then f of x1 is equivalent to f of x2. Sorry, let me say this again. Every time x1 is equivalent to x2, then f of x1 is equal to f of x2. Okay, let's be very careful. Equivalent and equal mean different things, right? So equal means being the same thing. Equivalent is some new rule that we have created, right? So x1 and x2 are equivalent, but f of x1 and f of x2 are equal. And, well, do we have this condition in this case? Well, yeah, here it is. We actually defined, we used star to define squiggle, right? Because in particular, we're using this direction of the definition of squiggle, right? The rightward direction of the definition of our equivalence relation is precisely the condition that we need to guarantee that square bracket f is a function, right? In other words, that if the equivalence class of an element x1 is equal to the equivalence class of an element x2, which means it's the same element in the quotient set, there's only one output for this thing. Great. Then we have to check that square bracket f is surjective. x mod tilde y is surjective or onto. Well, so how do we prove this? We say, okay, let y be an element of y. Anyone. Pick anyone you want, right? Now, what do we know? We know that f is surjective. Which means that either exists an x in x such that f of x is equal to y, so this y that we've picked right here, maybe let me call it y bar and y bar. And now what we're looking for is an element of the quotient set x mod tilde that is sent to y bar by square bracket f, but then we have it, right? Because we can use this x to make it. Square bracket x, the equivalence class that x belongs to, is an element in x mod tilde such that square bracket f of square bracket x is equal to f of x, which is equal to y bar. That's great. This is precisely saying that square bracket f is surjective. Lastly, we need to show that square bracket f is 1-to-1. So we assume that square bracket f of square bracket x1 is equal to square bracket f of square bracket of x2 . So what does this mean? What is the definition? Well, this by definition is f of x1 is equal to f of x2. And so again, let's go back and look at the definition of our equivalence relation. If we have an if and only if here, so in particular, if f of x1, we now use the leftward direction. If f of x1 is equal to f of x2, then x1 is equivalent to x2. But x1 equivalent to x2 means that the element of the quotient set square bracket of x1 is equal to the element square bracket of x2. And so we've showed that if square bracket f of square bracket of x1 is equal to square bracket f of square bracket of x2, then square bracket of x1 is equal to square bracket of x2, which is the definition of being 1-to-1. And so this concludes the proof that square bracket f is a bijection. Okay, so I encourage you all to look over the notes later and notice that we've really used everything, right? So we've used the leftward direction of the definition of the equivalence relation squiggle to show that square bracket f is a function. We have used f being surjective to show that f bracket is onto. And we have used the leftward direction, the leftward direction of the closed relation to prove that f is 1-to-1. Okay, any question, comments? Does this make sense? Give me a sign. Thanks, Tyler. Makes sense. Okay. Very good. Well, so excellent. So the next unit will actually keep building on these ideas. We'll take them, actually a couple steps further. So make sure that it continues to make sense until next week, because we'll be actually boosting this up, but we're not abandoning it. Okay, cool. Well, thank you all very much, and I will send you the link to this notebook, and I will also post the video as soon as it's processed. Thanks.
Lorenzo, can I ask a quick question?
Yeah.
My group was just curious. So for the group work, do you want an additional half page of summary on top of like our Google Docs sheet?
Yes.
Or, oh, you do? Okay.
Right? So I've said in the email, right, there's 3 things I expect from the group work, right?
Mm-hmm.
One is that every problem should be worked on.
Mm-hmm.
The second thing is that if I make corrections on the group work, they're somehow addressed.
Yep.
Show me that you're understanding what the correction is. And the third thing is I like a little summary of the work. Yeah.
Okay.
Absolutely.
Can we just attach that summary like at the end of if we just at the end of that Google Doc, could we just write it at the end of that? If
you
we
can
have
put it at the end of the document if you want. Yes, that's
okay.
fine. So long as it's
Sweet.
somewhere, right? So last week, only one group made the summary. The others sort of assumed that the worksheet would be enough, but I want the summary.
Okay.
Okay.
Good to know.
Cool.
Yeah.
Great.
All right.
Thank you.
You.
See you on Tuesday. Bye, everybody.